Welcome to this explainer. Look, if you're still picturing a clunky, desktop machine slowly oozing out a jagged plastic tugboat while making sounds like a dying dial-up modem, well, you're in for a massive shock today. We are going to completely shatter those outdated perceptions. Right now, we're exploring a hyper-fast, AI-driven reality that's literally reshaping aerospace, global sustainability, and even the future of human biology.
For a whole decade, additive manufacturing was totally changed to one massive bottleneck: speed. Back around 2015, hitting 60 millimeters per second was considered a huge triumph. But look at where we are now. That old barrier is completely gone, replaced by breakneck 600 millimeter per second speeds with accelerations nearing 20,000 millimeters per second squared. To put that into perspective, the physical machine isn't the bottleneck anymore. The bottleneck is literally just how fast we can feed it instructions.
Section 1. The AI and Speed Leap. How software rebuilt a machine.
It's actually software and AI algorithms, not just the hardware, that completely flip the script here. These smart printers, they don't just blindly lay down material anymore. They actually think while they work. Machine learning uses neural networks to watch prints in real time, catching microscopic defects layer by layer before the part is even finished. Meanwhile, AI-driven generative design is creating structural aerospace and automotive parts up to 70% lighter than what a human engineer could ever dream up. We're basically letting the algorithms evolve the most efficient shapes possible.
Section 2. Polymers and Sustainability. Rethinking Everyday Plastics.
What's truly fascinating is how these incredible printing speeds perfectly align with the massive global shift towards sustainable production. Think about traditional subtractive manufacturing for a second. You take a solid block of titanium or plastic and you just carve it away. You can waste up to 90% of that raw material as scrap. Additive manufacturing completely flips the script. It uses exactly what it needs, allowing up to 98% of the unused powder to be swept right up and recycled for the very next batch.
And hey, this isn't just a theory. It's transforming real businesses right now. Mark Joyce from Mag Orthotics totally hit the nail on the head when he said that moving to powder and TPU means there's practically zero waste. But beyond just saving material, this shift drastically cuts down our reliance on complex global supply chains. When you can print exactly what you need on demand right in your local facility, you don't need to fly components across the globe or store them in giant energy-hogging warehouses.
So the takeaway here is that even the printing hardware ecosystem itself is getting remarkably greener. Companies like Formlabs are rethinking their entire footprint. They've recently slashed the plastic use in their Form 4 series resin cartridges by an impressive 66%. We're seeing this amazing holistic approach where the technology doesn't just build sustainable parts, it actively uses sustainable packaging and supply chains to get the job done.
Let's move on to Section 3, Extreme Metallurgy, Forging Titanium Superalloys.
Okay, let's leave plastics behind for a minute and dive into the wild, microscopic physics of aerospace metals. We basically rely on two very distinct methods to build these titanium superalloys. First up is powder bed fusion, where a laser or electron beam traces incredibly fine, precise details into a bed of metal powder. It's absolutely perfect for complex internal geometries. On the flip side, we have directed energy deposition. Think of this one like a highly advanced robotic hot glue gun for metal. By using an electric arc to melt a titanium wire, this absolute beast of a process can deposit kilograms of material an hour, which makes it perfect for massive structures like airplane wing ribs.
But let's zoom in on the microscopic physics happening inside that powder bed fusion process. The localized heat from the laser is incredibly intense, obviously, but what truly dictates the final properties of the metal isn't the heat, it's the astronomical cooling rate. We are talking about the metal flash cooling at a rate of 1 million degrees Celsius per second.
Because of this hyper-fast, rapid freeze, the metal atoms literally don't have time to arrange themselves into their preferred stable crystalline structures. Instead, they get locked into a highly strained state known as alpha prime martensite. If you look at it under a microscope, it looks like a bunch of fine interwoven needles. Now, this martensitic structure is incredibly strong, way stronger than traditionally forged titanium. But it has one fatal flaw: it's highly brittle. It has really low ductility, meaning it can just fracture under stress without much warning.
Which leads us to Section 4, Perfecting the Printed Metal, Fixing the Flaws.
So we've got a pretty high-stakes problem on our hands. Alongside that brittle metal, the printing process can trap tiny gas bubbles, leaving microscopic pores inside the part. It's kind of like the bubbles in a carbonated drink. Those pores act as stress concentrators, practically inviting fatigue cracks. So how exactly do engineers take this stressed, flawed, porous titanium and transform it into components that are safe enough to fly in commercial jets or be permanently implanted into a human spine.
The fix is all about post-processing. Think of it like a deliberate thermal training montage for the metal. First, a stress relief anneal relaxes the internal tension so the part doesn't warp out of shape. Next, a high-temperature heat treatment forces that brittle, needle-like martensite to actually decompose and recrystallize into a much tougher, more flexible structure.
But the ultimate superhero move here is hot isostatic pressing, or HIP for short. Engineers place the part into a specialized furnace that basically acts like a deep ocean pressure cooker. It blasts the part with an inert gas at 900 degrees Celsius while simultaneously squeezing it from every single direction at over 1,000 times atmospheric pressure. HIP physically crushes any microscopic voids out of existence, totally welding them shut and creating a perfectly dense, incredibly resilient piece of titanium.
Let's completely shift gears now. Section 5, the biological frontier, printing living tissue. If you thought extreme metallurgy was mind-bending, welcome to the world of bioprinting. Instead of melting metal or plastic, researchers are formulating what they call bioinks. These are highly advanced fluids that actually suspend living cells inside supportive biomaterials, things like natural collagen, gelatin, and hydrogels. The printer meticulously builds living tissue scaffolds layer by layer, providing this hydrated environment that mimics the body's natural matrix, and it does it all without crushing those incredibly fragile cells during the process.
And let me be super clear, this is not science fiction. Researchers at places like the Wake Forest Institute for Regenerative Medicine are already seeing massive 85% cell survival rates when they print structural tissues like ear cartilage. Today, the pharmaceutical industry is actively using these bioprinted tissue organoids to test new drugs without relying on animal models. It's giving them way faster and far more accurate human predictive data.
There is, however, a pretty major biological roadblock here. If you want to print a fully functioning transplantable organ like a kidney or a liver, you hit the 200 micrometer wall. 200 micrometers is roughly twice the thickness of a human hair. Once a printed tissue gets thicker than that, the cells deep in the center just can't get enough oxygen by diffusion alone. They literally starve to death unless we can somehow figure out how to print a highly complex capillary blood supply right alongside them.
To bust through that biological barrier, material scientists are completely moving away from static materials and developing smarter, active hydrogels. These next-generation bioinks actually respond to their environment in real time. Just imagine glucose-responsive hydrogels printed right into a diabetic wound that actively sense local blood sugar levels and then adaptively release insulin to speed up healing. Or what about self-healing hydrogels that can autonomously repair their own structural damage using dynamic chemical bonds? It's absolutely wild.
And that brings us to our final stop. Section 6, the fourth dimension, time and shape shifting.
Building on that idea of active materials, we reach our most profound frontier, 4D printing. Now, there's no magical fourth spatial dimension here. The fourth dimension we're talking about is just time. We're engineering materials that are programmed to autonomously shift their physical structure over time when they're exposed to specific external triggers, things like heat, light, pressure, or moisture.
Pioneered by places like MIT's self-assembly lab, this isn't a magic trick. It's just brilliant material science. You can print a completely flat tile, which, by the way, makes it incredibly easy to transport, and then you simply drop it into water and literally watch it physically fold itself along pre-programmed lines into a completely new, complex 3D form.
We have covered some immense ground in this explainer today, haven't we? We've seen algorithms practically designing themselves, lasers flash freezing metal at 1,000,000 degrees a second, living human cells organized into beating organoids, and matter engineered to fold itself over time. So, I want to leave you with this one provocative thought. If we can harness AI to print everything from flying superalloys to living tissue to shape-shifting matter right now, what incredible reality are we gonna print next?